Hey guys, welcome back to the series. In this episode, we're going to be working on our type infrastructure. So in the last episode, I really just did like a broad overview of everything that we're going to be doing. So I suppose we should probably just start working on the implementation now. And one thing I will say now, before we even write it, and I've said it before, this is pretty new code for me. It's as opposed to like the parser and the lexer, which is a design I've sort of worked on for, I don't know, like over a year at this point, and I've sort of like come to terms with and I think is pretty solid. This is like relatively new because I'm reworking something that I had before that didn't really work because my issue previously was I tried to do all the transpilation and type checking all in one big step, and so I had a thing called a T expression, so like a transpiler expression, and that had to store the like constant value, it had to store the type, and it had to like manage actually like building the code for the transpiled language, and that was just all too much. So this is sort of stripping away just the type part from that. So in the future, we may end up refactoring or adding new things to this. So I'm just letting you know now. Okay, so let's go into, I think, our grammar package. That's the word. I didn't want to say module. And I think it should be in here, approximately. Like, that just kind of makes sense to me, even though it is sort of part of the grammar. It's certainly part of, like, the language rules. So if you want to separate this out from the rest of the grammar, you can, and maybe we'll do that in the future. But for now, we can just begin work and make a BasicType.kt file. Okay, package c.grammar, as per usual. Now, we do need one specific thing. Normally with enums, which we're going to be using to represent the types just for like, because it kind of makes sense. Before I've used strings, which is like fine, but it just feels kind of hacky because you could enter a string with kind of anything and the compiler is it's just going to make a mistake instead of actually warning you. So I've moved to make it more of an enum. And usually you'd use capital names for like an enum. I don't know what a boot is. It's a fancy type of bool, I guess. A double boolean. But in this case, I just want the names to be one-to-one with the actual keywords for our language. This helps us for a few things. One, it's just easy to remember when we type it out. Two, it allows our toString to just give the name, which is very nice, and we don't have to like convert it if we want to print it out. But of course, this is going to cause some issues because a lot of these keywords are already defined in Kotlin. Things like bool and char and int and whatever. And the good thing is that only matters inside of the enum. Outside, it's not going to affect it because we'll always access one of these types by saying BasicType.int, for example. So there won't be a namespace conflict outside the class, but there will be inside. So the issue is, if you see on the right, we're going to give everything a casting priority, which is an integer. But if we just said int, like this, the compiler is going to give us an error because it thinks we're talking about the enums int. So all we have to do is we just have to make a type alias, and I'm making it private because I don't want everything in my project to be able to access this because it just doesn't need to. It doesn't really matter if they could, but it really just needs to live in this file. And then we can construct our enum class, which I'm just calling a BasicType. And like I said, it needs a priority, which is of type, in this case, kint for Kotlin int. And now we can actually define our types. And these should be familiar from what we've discussed before. So things like booleans, characters, and you can kind of arbitrarily choose your casting priority. But the way I'm setting it up is, if you don't want something to be able to be implicitly casted, it should have priority -1, meaning essentially the idea, like I've discussed before, is if I have 2 plus 1.3, 2 will be implicitly casted to a double, and then it will be added, and you'll get a double result. That's how I'm choosing to make my language work, but you can make your decisions for your language whatever you think is best. A lot of languages don't have any implicit casting, in which case you wouldn't need a priority at all. But yeah. So we have bools, which are obviously going to be like the lowest sort of thing because they're the smallest number, and then characters as well. Nat8, int 8, you'll notice I jumped up from 2 to 10, which it's arbitrary. But like I mentioned before, nats need a lower priority than ints because there'll be certain, because imagine if the default integer were a natural number, then if you did 3 minus 4, that would have to be a natural result in that it would be -1, but it would be -1 in terms of like the 2's complement without the first bit being a sign bit, which would just be weird. And you'd have to do a lot of casting to int explicitly, which is kind of annoying. So yeah, my solution to that is unsigned integers just have a lower priority than their equivalent signed integer. And obviously, it's easy to cast between nat 8 and an int 8 because in memory they're just the same thing. It's just how you're inferring about them. But of course, both of those being only 8 bits should be less than a natural 16, for example, or an int 16. Although I suppose one consequence of this system might be if you have an int 8 and you add it to a nat 16, the result will be a nat 16. Which, maybe I'll change that at some point. Like, maybe it should be if you're adding an int to a nat, then it should always just be the int, but it needs to also keep the size. So if that turns out to be an issue, we'll probably come back and modify that. But either way, yeah, I'm just counting up with these numbers. It's really nothing too exciting. Int 32 is next. 17, sure. And then we have our 64-bit types, which are going to be 18 and 19. And 64. And hypothetically, depending on what language you're transpiling to or whatever, you could have different types. You could have exact width ints, for example. You could have a 128-bit int if you want. It all depends on how you're going to implement it. And then our reals are going to be 20, 22. Real 64 is 24. Again, pretty arbitrary. Jump up another 10 because a complex is kind of a big deal. And a Cplex 64, 34. Okay. And then we need 3 other types. Although only one of these 3, as of right now, is going to actually have a type keyword. We're probably going to change this in the future, but I suppose it doesn't really matter because the only thing we have in our language so far that needs the keyword is casting, which we also really haven't implemented yet. But anyway, the goal is to just get something functional first, and then we can build on top of that. So we should have an any type to represent sort of information that could be anything. In my case, there's 2 ways you could go about like an any type, right? It could be sort of like a void pointer, and anything can be stored there. Or it could be sort of like, if you have a more dynamic type system, you could actually like, it could be sort of, it's like hard to explain, right? Because if you think about like in C++ has an auto, but that's sort of like type inferencing, and we're sort of just doing that implicitly. It's really just kind of like a void pointer, I guess. But for us, right now, that actually doesn't even matter. But in the future, we're going to add optional types and stuff. And so we're going to have a none. And when you write none, well, it doesn't actually have a type. It could be anything. It's just null. It's just optional. It's not actually like any type. So I'm going to give that a priority of 0. Because... why exactly? Because for assignment, if you're doing val x is of type optional int and you say none, in this situation, none should be of type any, and it should be implicitly casted to type optional int. Except, that doesn't mean that you can then implicitly cast during operations. Because we're just going to say, if you have an optional in an operation, then you just can't do that. You'll have to explicitly declare that it isn't optional, or do something else, you know? But anyway, that's getting ahead of ourselves. We'll also have a unit, which just represents returning control flow. It just represents a single value, a unit. And of course, we'll have strings. And these both cannot be implicitly casted to anything. If we allow operations on strings at all, it will probably just be appending them. And it would be appending them to other strings. So that's essentially just our enum. And now we want to have some nice useful fields on this so that we can just, you know, quickly determine stuff. So for example, we can determine, is this type a number? Well, in my case, because of the priorities I set out, I can just say if the priority is between 1 and 34, then it's a number, because that means it's between a bool and a Cplex 64, so it's a number. So this is sort of like magic number. Hypothetically, what you could also say is Cplex 64.priority, if you wanted to be sort of rigid about that. But in my case, if I modify any of these priorities, I'll just have to modify these as well. But it's all in one place, so I'm not too miffed about it. So we can also say, well, is it an integer specifically? And in this case, I mean signed or unsigned, so I'm going to say 1 to 19. And now here's like sort of one of the big ideas. When can we operate on a type? Well, how about the type manages that itself? So we can just have a field that says can operate on. And in principle, this could just be a property, but I'll show you what happens if we make it a property instead of a field. So when can we operate on something? Well, if it is not in the list of types that are any or unit, then we can operate on them. And I'm saying that because there might be some string operations we'll be able to do in the future, but we can't operate on an any type and we can't operate on a unit type. And you see, if I do this, it says enum entry unit is, and it's going to be like uninitialized here. And that's because it's interesting, right? Because this property is going to be defined, I guess, kind of at the same time. So it's like there isn't a guarantee that this would be defined. So the way we could fix that is we could just make it a getter, which means this will be evaluated at the time when we call it rather than, at like construction of the enum class. We can also override the toString and it can just return the built-in enum property name, which will just be, these actual names that we've typed out. And now we can actually work on a bit of toolkit. So like I said, this whole thing is designed around implicit casting, at least for now. So let's develop a method called implicitly cast_to. Oh, I missed a lot of letters here. Implicitly cast_to. And the idea here is it will attempt, if you give it a type, then it will attempt to implicitly cast the current type to the given type. And so, what do I mean by attempt? Well, it might fail if you can't implicitly cast it to that, right? So the return type is going to be a nullable basic type, because if it succeeds, it will return the new type. If it fails, it will return null. The way I've designed this whole system is sort of around the concept of immutability. So you could just design this sort of system where you have a type, and then the type has like a value bool, and then when you cast it, it modifies the object and gives it a value of like string or something. But in our case, we're going to just be passing around the same like 20 objects instead of modifying them. So it's just going to be like immutable data being passed around instead, which is why we're doing it this way. Okay, so obviously, if this is the type, if we're casting something to itself, that is always valid. You can always implicitly cast something to itself, even a unit, even a string. Now, otherwise, we're casting between two different things. So if our priority is less than 0, well, we can't implicitly cast this, in which case it's a unit or a string right now. Unless, of course, you add other things in the future, and we will. And then the last condition, if you are able to actually implicitly cast, well, that's only true if your priority is less than or equal to. In this case, we already checked the equals, because only the same types have the same priority, unless it's -1. So in this case, the only time you can implicitly cast something is, for example, an int to an int32, because the int priority is less than the int32 priority. So we can simply return if the priority is less than the type's priority, then we can return the type. Otherwise, we return null because we simply can't do that cast. And then in the future, we'll be able to handle a null value to know that it means that the cast failed. And that's kind of the utility of optional types, which is why we're adding them, because you can just do things like this. for essentially error handling without actual errors. You can just say, well, this failed, so we'll just return null. Instead of needing, like, another thing you could do if you didn't have null is you could just have some, like, some default type here, or like a none type, or like a fail type that only exists to act as a null. But that's kind of dumb. So we're just going to use null in this case. Then, like I've discussed before, there will be times when you want to implicitly cast things. For example, if you do a bitwise operation on a Boolean, so like true and true, well, if you're doing bitwise operations, you're dealing in bits, so you're really dealing in a natural number rather than the actual, like, abstracted concept of a Boolean or a character. So we would want to implicitly cast up from that. So we can create an implicitly cast up to. So before we were implicitly casting to, now we're casting up to something. Meaning, if we're already above it, we do nothing, but otherwise we cast up to it. Again, it takes a basic type and it returns a nullable basic type. It's going to be, essentially, it's pretty much the exact same thing. This is an example of where you could, like, refactor it and pull out the commonality, but I find that especially, it's 3 lines, right? We're copying 3 lines and changing one thing in 2 functions. I don't see the need to refactor that, and I think that would be unnecessarily coupling them, because that's the issue with, like, making common elements to code. You unnecessarily sometimes create too much interdependency, and that makes it harder in the future. So if we ever get to the point where we have a reason to refactor this, we can. But I think a lot of the time when we just see the exact same thing, we just think that would be better if it were in some separate function with some higher, like, thing. But in this case, I don't actually think that's going to really help us much. At least not yet. But yeah, the first 2 conditions are identical. In fact, the last part's identical, except instead of returning null, we return ourself. Because the idea is, if they're the same type, you're fine. If you can't implicitly cast, then you're not fine. But in this case, where if your priority is less than the type, that means you can implicitly cast up, so we'll return the type. But otherwise, well, what does that mean? It means that our priority is higher. So it would be like we're implicitly casting up to a Boolean from an int64. Well, an int64 is already above a Boolean. So instead of returning null, because we're not trying to cast to the bool, we're trying to cast above the bool, so we can just return this. I hope that kind of makes sense why we're doing that. Because we're just going up to a point instead of exactly to a point. It's also going to be useful to be able to convert naturals to integers. So for example, one of the implicit casts my language is going to do is if you have 5, and if you have 5, that's a natural number. Like, you actually store it as a nat, right? If you actually sort of, like, do this, then if you use that variable as, like, plus, like, x or minus x, well, clearly you're dealing in the sign, so you need to actually cast it. I do think I will have to actually mess around with this priority system, because now that I'm thinking about it, there needs to be something, like, I think that criticism I talked about before, where, like, integers, an int16 could be casted up to a nat, which would get rid of the sign information, which would be kind of weird. It really just needs to be like, if you did an int16 plus a nat32, that should probably give you an int32. So I'll have to probably tweak that and then work on that system. Let me know what you guys think, because to me that seems kind of unintuitive, right? That you would have an int32 plus a nat64 and get a nat64. Because what if your int32 is like negative 1,000 and your nat64 is like 5, and then your end result is still going to be a natural? And fundamentally it doesn't matter, right? Because they are the same in memory, so making an int64 doesn't really matter. I don't know, unsigned ints are kind of just weird in general. But I probably should make it so that when they interact with ints, the result will always be an int that has a sign on it. Okay, so like I said, sometimes there's times when we want to make nats sign, so we can just have a map, essentially, that is the result of this. When it's a nat 8, it should be an int 8, and it's just, you know, the exact same thing for the other sizes. Except I also missed one, didn't I? Because a nat itself needs to go to an int. I did forget that one before, but that's good thing I remembered it now. Yeah, let me, nat should go to an int. Okay. And lastly, for this, we want, like, to be able to operate on two separate types. For example, if you're doing a plus operation, any sort of arithmetic, we just want some general thing to sort of do what we were describing, which is one of the types needs to be implicitly casted to the other. But we don't know which goes to which, because you could have, like, 3.0 plus 1, or 1 plus 3.0, but the end result should be the same. 1 needs to be casted to real, or whatever version of real this type is. Doesn't matter which side it's on, so we have to make a method that handles that. That isn't really a property of the class, it's more of a property of types in general, so I'm throwing it in a companion object to make it static. So we can call this, like, operate on. And it's operating on two different types. A T1 and a T2. Often this will be like a left and a right thing. And they're both basic types, and just like before, we'll return a nullable basic type so that if it fails and we can't operate on them, we return null. And how do we know that we can't operate on them? Well, if we can't operate on type 1, which is why we made this can operate on field, we can't operate on type 1 or we can't operate on type 2, then we return null. So if we can't operate on both of them, then we can't do this, right? But otherwise, if we can, then what we can do is we can return t1 dot implicitly cast to t2. And now, if this cast failed, what happens? It returns null. And if it succeeds, it returns something that isn't null. So we can just use this operator in Kotlin so that if this isn't null, we just return it. And if it is null, then we can try this. T2 implicitly cast to T1 the other way. And again, if this fails, the whole thing will return null. But as long as one of them succeeds, that type is going to be used. And so it's just this neat little small thing. And at least for now, that's how this works. But like I said, I do think I'll go back and make modifications so that it's a bit more intuitive with how stuff works. As far as I know, complex numbers are required as part of the C standard, as far as I can see. And of course, C standard being, you know, C, the language we're transpiling to, not the language that we're making. I hate myself for making this name every day. Since it's part of the C standard, I may as well add it to mine. It's really optional, right? Like, how often do you use complex numbers in a language? Like, not very often, but it's nice for things like trig or different mathematical stuff, finding square roots of numbers and stuff. Hypothetically, what I could do is that's really the big reason I'm adding implicit casting in the first place. Because without implicit casting, how am I supposed to write complex numbers of this form, right? Because it's like, okay, 3i, that is a complex number, but then we can't add an integer to it, right? Really, what I want this number to be is 1.0 plus 3.0i. But if I write it like this, without implicit casting, it doesn't work. So that's why I'm adding implicit casting. Plus, I just think it makes sense to be able to add an integer to something that isn't an integer and have it work. Because, like, that just makes sense. I don't think that's a mistake, you know? I don't think forcing me to say this actually helps the understanding what's going on. So I'm just going to do that, but I'm going to make some modifications to the thing. In fact, I think there should be backwards compatibility with the nats and ints. So for example, if we have a nat and we do this, this should work. But the way I have things set up now, it won't, because 5 is an int and the int cannot be implicitly casted to a nat. But I actually think nats and ints should be implicitly castable to each other. And when you add nats to ints, when you operate on an int and a nat, the result should be an int. At least in most situations, right? Maybe in a bitwise situation it shouldn't be, but I'll have to worry about that later. And then, of course, the more implicit casting you adding, the more like strangeness you add to your language that people have to learn. Which is one nice thing about a language like Rust, where you don't really have implicit casting to other things, at least as far as I know. A language like Kotlin, where you'll notice where if I do like if I want to do 5 to the power of 2, I have to say 5.2 double, and then I have to do .pow, and then I have to do 2.2 double, and then I have to do .2 int at the end. And like, that's stupid. I just think that's stupid to me. In my language, I would just want to be able to say 5.pow2, and it should figure it out. You know what I mean? I don't see how those explicit casts make the code more readable or like less error prone, because to me they make them more error prone because I don't know what is actually happening and I can't read the line. So I'll have to figure that out. But for now, I think this is a good framework. It's not going to be worthless to write down now because I'll probably keep the majority of it. I'll just have to add some extra rules for implicit casting between nats and ints in the future, I think. So let's work on expression types. I will give you this sneak peek on expression values. If you can figure out exactly like why or what it's doing. I did talk about what we'll be doing later, but yeah. Okay, expression type. And as I've mentioned before, this class is going to be very similar, but it's going to retain extra information. We need to know if a type is dynamic, and we need to know if a type is optional. Technically, for our implementation of the language, we only need the basic types right now, but in the future, we will be adding more features, so I'd rather just set it up as is and not have to go back and refactor a bunch of basic types to expression type. So let's go out, actually, straight to here, and let's create a new file, expressiontype.kt, just keeping things organized. Of course, you can organize things however you want. It's part of the C grammar package, and we can make this class called expressionType. Now, this is going to be pretty wide, so I'm going to split it up on multiple lines. First, it's going to have a B type, which is just a basic type. I'm just calling it a B type because I'm too lazy to type basic every single time. So it's of type basic type, and I could just call it like type, but expression type sounds confusing to me. Expression type basic type makes more sense to me because it's like the expression type is composed of this thing, but just calling it a type doesn't seem like it's enough information in my opinion, but you can call it what you want. If you just want to call it type, that should be fine. And by default, if we're making this expression type, the basic type should just be unit, because that's sort of what everything is, so long as it's returning control flow. Things like functions or if statements or for loops, in my case, are all going to be of type unit, because they do not, the only thing that they don't return a value, but they return control flow. Next, we just need a Boolean to see, is this a dynamic type? Is this type supposed to be stored on the heap or in the stack or somewhere else or not or whatever? And then optional, which is very similar to Kotlin's nullable. In fact, it's basically the same thing, except it's not null because I'm not directly dealing in pointers in my language, at least not yet. And so it essentially just stores those three things, and it has some default values on there. Now we can begin by just overriding toString, which will return string, and we can just start by building this thing. So our result can be, we could start with just the B type, which is just the enum's name, so something like unit or char or int. And then if the type is dynamic, then result can just be equal to hash result. So we're just prefacing it with the hash symbol, which is how we make a type dynamic in our language, at least for now. And similarly, if it's optional, we could take the result and we can append a question mark to the end. And the way we're doing things, if they're both optional and dynamic, this will work. And then, of course, we just need to return result. So that should just print out our types. Perhaps you want to add other information to your types for some reason. You could essentially just add another property and then add that in there. It shouldn't be too crazy. Similarly, it would be nice to have a canOperate property for these expression types. And like I've also said, you'll notice everything here is a value. These expression types also cannot be modified. You just create a new one, which might not necessarily be the most memory like efficient thing. And you could implement it as like immutable. It's just this is for me the way I'm designing this. I think I've done mutable in the past and like it's fine. But I think this, I don't know, maybe I'm just like on some immutability like craze or something. But so when can we operate on an expression type? Well, firstly, like I've said, if it's optional, you can't operate on it. Just like in Kotlin, if you have 5 plus, okay, how about we have val x of type nullable int and it's 5. If you say x plus 5 or x plus 2, there's not going to be a problem here because this isn't like in a function test. But here you go. Because what the operators do in Kotlin is it's actually calling methods, but you can't just call a method on a nullable thing, because what if it's null? It doesn't have the method. In our case, we're conceptually doing that, but we're not literally doing that, at least not yet. And so you can't add 2 to something that could be null. So how do you solve that? You have to do something like this. And then that's valid. So we can't operate on something that's nullable, in our case optional. So we can operate on it if it isn't optional, and if the B type is operationable, if we can operate on the B type, the basic type. Now, when it comes to the dynamic property here, it's sort of just there. It's not really, at least for now, we're not really going to care about it, because it's really kind of just, it's for like references and stuff in the future. It's not really going to affect anything now. Then it would be nice, like I've said, since this is an immutable thing, it'd be nice to have a way to copy them pretty easily. So it could take a B type, which is a basic type, but in my case, I'm going to make all of these optional, all these nullable. This is a Boolean. And the reason I'm making these nullable is so that if you pass in null, what you're telling me is you want it to be the same. And if you pass in a value that isn't null, you want that to be the new one. Because we're copying something. So if you don't want to change part of it, then you don't have to pass in every single piece. If you only want to change the B type but keep everything else, you can pass in, you could just say copy B type is equal to basic type dot real or whatever. And then that wouldn't modify the dynamic or optional components. And so obviously, the way we'll do that is using the Elvis operator, the null coalescing operator. Yeah, that's it. And if you gave a value, we'll use that. Otherwise, we'll just use the existing one. And we're constructing a brand new instance of this as well. If dynamic is null, then we use the existing one. If optional is null, then we use the existing one. Otherwise, we use the one they gave us. Now we sort of need extensions or pass-throughs of those methods that we made for implicit casting and stuff. Because there's more information now. The fact that this thing could be optional affects whether we can implicitly cast or not. Because you can't implicitly cast something that's optional to something that isn't optional. It would be like, well, for example, if you have val x of type int, you can't give that the value of null. Because in the way I'm thinking about it, null can't be implicitly casted to type int, but it can be implicitly casted from type optional any to type optional int. So implicitly cast to some type, and in this case our type is actually an expression type, and the type we're returning is an expression type. If our type is optional, but the type that we're trying to implicitly cast to is not optional, then we can't do the cast and we just return null. Otherwise, we should implicitly cast the B type, type.btype. We'll implicitly cast the B type, and what that means is, well, if that cast fails, we want to return null. And if it doesn't fail, we want to return a copy of this expression type. So we can use this null safety access operator, because if btype is null, we'll just return null. Otherwise, we want to return this value. Actually, I guess I could just do this, couldn't I? No, I can't, because I don't want to ever return the btype. If the btype is not null, then I need to use it to modify, and we'll just create a copy of this expression type that uses that new btype. Otherwise, it returns null. Similarly, I don't know why I can't type today. Implicitly cast up to. It's like, what's the point of being able to type 100 words per minute when your brain can't actually do that when you're trying to code? Implicitly cast up to, basically the same sort of deal. In fact, it actually is the exact same thing, except instead of saying implicitly cast to on the btype, we'll be implicitly casting up to on the btype. But yeah, if this is optional and the type is not optional, we cannot do this. Otherwise, let's cast the btype. In this case, it's implicitly casting up to type.btype. And lastly, if that cast fails, we return null. Otherwise, we want to copy this expression type and give it the new btype to use. Okay. Now, let me look at what is there. Okay, yep, so now I have an override for this implicitly cast up to. So instead of taking an expression type, we could actually just take a basic type, because maybe all we want to do, maybe we don't actually care about the rest of that, right? Like if we want to cast up to a nat something, we don't necessarily need to construct an entire expression type to do that. So let's just have this overload, and it's pretty simple. We could just call implicitly cast up to, and we could just make a copy of our current thing and pass in the btype, which is admittedly a lazy way to do it, because then we're adding a new object to memory. But it should do what we want it to. And we want to pass through make int signed. And this is just so we can avoid calling copy on the btype. So what we just do is btype make int signed. But otherwise, we just copy everything and return a new object. Maybe we could make this mutable in the future. I don't know if that would actually be an improvement, or if this is like bad or whatever, but like I said, this is all very new. This is kind of like first and a half draft for me, so we'll probably make some changes in the future. Lastly, we need another operate on thing. Just like before, inside a companion object, we have our first type, which is an expression type, but this time, our second type is actually optional, and it defaults to null. So the reason I'm doing that is I want to still check if I can operate on this thing, even when it's a single, even when it's a non-binary operation. Although now that I'm looking at this, I don't really see the need for that. Why did I choose to do that? Because I already have the can operate on field or property up here. So I don't need to say, I guess, let me see, what would it look like, right? If I have a type, I could say operate on, well, in fact, it would be expression type.operate on my type. And that would be the result. Otherwise, what you'd have to say is type dot can operate on. Actually, you'd have to say if type dot can operate on type else null. So I guess that's why I did it. It's just for, like, it's less writing. Yeah, I'll still do that, but we really don't, like, necessarily need it, but yeah. We'll just allow it to work for both binary and unary operations. So if T2 is null, Well, then we just want to return if T1 can be operated on, T1 otherwise null, which is exactly the thing I wrote before. It's just less typing in the future. Otherwise, it's very similar to the lower level one. If we cannot operate on T1 or we cannot operate on T2, then this whole thing fails and we can't operate on both of them. Otherwise, we can just implicitly cast one to the other. Implicitly cast to T2. But notice that even though it looks the same, we're actually calling these implicit cast functions up here instead, which has the extra optional information check. Okay. I may end up in the future merging these two classes into one thing because it kind of does feel redundant, I will admit. But yeah, I'll have to worry about refactoring at a future time. I think we're 40 minutes in, but I think I can probably still do the verifier. Because it's not actually that complex. Yeah, why not? Okay. So now actually we want to go out to our stages. We want to create a verifier.kt, package c.stages, because this is our next stage. And essentially this is just a toolkit to allow us to operate on, this allows us to do our type checks. It allows us to do value stuff and borrow checking in the future, but we're not there yet. In fact, I haven't written that at all. And the reason we returned null before is because we didn't have a node to sort of give an error to, right? But this is where we're actually going to be handling our errors, which means we need access to a false object. We want to import nodes from our grammar. We also want to import our types. Now we can make this data class, verifier. I don't remember if I actually have a good reason for making it a data class. Again, I'm not very sure of why to use a data class over a normal class. But anyway, this is a stage, so it's going to take a false object, and it's going to have the tree that was created by the parser. In this case, I'm just going to make it private because you don't really need to access the tree through this for anything. And what I want to do is I want to create a stack so that one of the issues I've run into in the past when making type checkers and stuff, since we're like parsing the tree, if I'm making a toolkit that every node is sort of like inheriting through a function, the way that we've been doing like everything, well, that means every node has access to the toolkit, but the toolkit doesn't have access to every node. So if you have functions in the toolkit that throw errors, you have to like pass in the node as part of the function so that it can be passed to the false object as a fault component so it can be marked. So my solution to that is I'm going to essentially build a stack while we're verifying that will keep track of the latest node to call the verifier. And so if that node causes an issue, we'll have access to it to give to the false object. And in order to make a stack in Kotlin, we want to use an array deck, which is, it's like an array list, but it's optimized for adding and removing things from the end of it, which makes it good for being a stack. Since essentially the only operations we're doing on the stack is adding something to the end and removing it from the end. So we can slowly build up a stack of nodes, and it would be nice if we could access the latest one pretty easily. So I'll just create a field called node, and that's just nodes.last. Nodes.last isn't necessarily hard to use, but I still think calling it node is kind of nice. And then what we want is sort of the introductory method into this. If you remember to like our parser, we had a make tree function. In our lexer, we had a make tokens. So for our verifier, we're going to have like a verify tree, which is like the root sort of method that will be called. And in the future, this will call tree.verify node, passing in this verifier. We haven't actually written that yet. I'll go do that right now. Let's just save this and go. Actually, let me just do this and go up to our node. And let's go down to the bottom here. We're going to need 2 verify functions. And there's a reason for that. Like I've said, we're building a stack of nodes. And it would be kind of annoying if every single time we were making a verify function that we had to manually append this node to the stack and then remove it at the end. So why don't we just have a method that does that for us? So at the bottom of our node, we're going to create a verify node. And this will be the actual thing that verifies stuff. But we won't override it. This is just the implementation for every single node. It takes in a verifier, and for now, I don't think it needs a return value. We might add that in the future, I'm not sure. But essentially, this is going to take the nodes, and it's going to add to the end this. It's going to append this thing to the end of the stack. And then what we need to do is we need to verify. We need to call the verify function, but it's also kind of annoying in every verify function to verify all your children at the same time, because that's just sort of, it's the thing you'd have to do every single time, right? If you have an additive expression, you have to verify the left and the right node every time, and that's kind of annoying. So what we can do, and I'm pretty sure this works, I haven't exhaustively tested this, so this may cause errors that we'll have to come back and fix. I'll create a new list of all the nodes, all the subnodes of this current node. And what I'll do is I'll take all of our parts, which are nodes and tokens. I'll map not null, because some of them could be null. So let's remove everything that's null. And then I'll say it as node. Actually, do I even need that, I don't know if I need that, because I'm doing map not null. Because I'm trying to map it. I think that's sort of like saying if the cast fails, it returns null. Okay, so I think I see what's happening here. When a cast normally fails in Kotlin, it just throws an error, but I think when you use the as question mark thing, if the cast fails, it returns null. And so we'll be casting everything to a node, and then all the tokens that are there will be casted to a node and return null, and then the result of the map not null will then remove everything that's null. And obviously, if we're casting null to a node, that's also going to fail. So at the end, we'll just get a list of every single node. Okay, I think I see how that works. And then nodes.for each. Then we just want to loop through each of them, and we just want to say verify node. And again, like I said, we're using the verify node function here for this. Otherwise, once all of our previous nodes are verified, we can verify using the verifier, and the verify is something we'll manually overwrite in every single node. And so you see this is just recursive. And then once it's done, we can remove this node from the list. And because of the way this works recursively, you'll always know that this will always be the last thing, right? Because anything here would have already removed. Okay, and then we can come up to, where would I put it? Up here. So we have our construct, but let's now make an open function because we want to be able to override it in subclasses. Call it verify. It takes a verifier. And all this is going to do, well, we're going to have to override it, right? So you could make this abstract. But in my case, I'm going to just give it a default implementation. But so what is this thing supposed to do? What's the goal of the verify, at least for what we're dealing with? Well, what we want to do is we want to figure out the type of the node. And it doesn't return anything, though, because it could return the type, and you could do things that way. But what I'm going to do is I'm going to create a late init variable called ExprType, of type ExprType. It's late init because it's going to be defined once verify is called. And it will only cause an error if you try and access it before it's initialized. But we'll always access it after it's initialized, after the verify has been called. So by default, what verify should do is it should just set the expression type to a new expression type, which is actually just a unit. That way, when we have a ton of statement classes, we don't need to manually override verify every time just to set it to a unit. This is just the default implementation of that. But of course, in subclasses, we'll be able to come in here and override what verify does. And we won't have to worry about the node stack at all, because this is what's actually going to be being called everywhere. So I hope that makes sense. I think now we can go back into our verifier. Yep, let me update this. And it might not actually like fix itself for a bit, but that's okay. No, it did. Okay. So we can then add tons of useful tools, but I think that's probably going to be mostly it. What I just want to do now is, whoa, that's a lot of. Let me go into my app.kt file. I did the exact same thing on the other one. And let's just link in our verifier so that it can actually start doing stuff, which in our case is just going to be assigning every node to type unit. And that's also because we're assigning the value, we're storing it. So the question is, why are we storing it? Well, one, the big reason is so that we're going to need the type information when we transpile. So we should just have it as part of the node, so that once we transpile, we can say, okay, we need to use this built-in type because it's this type in our language. And because we're storing it, we can do that ahead of time verification for the child nodes, for example, so that we know it will just have this thing stored somewhere. We don't have to worry about a return value. So let's go down here and create a run verifier. It's going to be, very similar to these other ones. It's going to take in a verifier and a D file for debugging. I haven't figured out how I'm going to display the debug information. What I might do is I might print out the AST, but instead of like the nodes, it might just display like an AST of types and values. That might be sort of what it will end up doing. But we will then run stage. And this is slightly too long, so I'm just going to put it on this line. Verifier.false. And we just say verifier.verifyTree. And dfile, for now we're just going to write verified so that we know that this actually occurred. And now that we have that, we can essentially do the exact same thing we've done before. We can construct a verifier. It needs two things. It needs false and it needs access to parser.tree. And then if run verifier using the verifier and the D file fails, then we break. We return out of this. So let's try running this. It's always nice waiting for a large build. But it didn't fail. Nothing actually changed except it actually printed verified, which in principle means that the verifier ran, and it in principle means every node should have their type set to unit, essentially. So I hope that this episode was good for you guys. I definitely need to work on a little bit of refactoring, I think. If you have any suggestions, let me know. But I do need to, I think, change some of that implicit casting rules to be more intuitive. So, yeah, like I said, the earlier parts of this series were very, planned ahead, and I sort of knew exactly where I was going, but now I am really, sort of just, in the deep end, sort of trying to navigate, blind. So, there will be a bigger delay between episodes, because I have to actually design things from the ground up to make this work. But I'm still going to continue the series, and if you have questions, you can always feel free to ask. But you may have to wait a week, or maybe even 2 weeks sometimes between episodes. But yeah, all slowly but surely, we'll make our way there. So I hope you guys enjoy, and I'll see you in the next episode.